Good afternoon, everyone, and welcome to our webinar series called The Experts Speak in association with IABSC, the International Association for Business Analytics Certification. And we're glad to, we have our founder of IABSC, Mr. Hans Vogels, joining us from Netherlands today. And today he'll be introducing the speaker for today, Mr. Sasi Kumar. Over to you, Hans.
Okay, thank you, Ram. Welcome, I am Hans Volkers, founder director of IBEC, and I have the honor of introducing one of the leading authorities on the area of AI and data science, with an extensive theoretical basis, as well as a vast practical experience of how to realize AI in practice. To describe him, I need to explain a lot of abbreviations, which sound complicated. but you will find in the presentation that Dr. Sasi Kumar makes the material clear to understand for everybody, even if you do not have a deep technical background. I'm proud to introduce to you today Dr. Sasi Kumar. He's the Executive Director of CDAC, the Center for Development of Advanced Computing in Mumbai, a premier R&D organization under the aegis of MEITY, the Ministry of Electronics and Information Technology for the Government of India. After completing his BTech from IIT in Madras, he did his master's from IISc in Bangalore. And he also has a doctorate from BITS in Pilani. He has co-authored 2 books, one of it being from Prentice Hall on parallel computing, and was also part of the KBCS Nodal Center at NCST, working on expert systems, resource scheduling, logic programming, and generative algorithms. During his career, he initiated and nurtured several projects on AI and e-learning, like the OLabs project, which created more than 200 virtual labs for schools during the COVID-19 pandemic, receiving widespread appreciation from CBSE and NCERT. He's also on the program committee at several international conferences. Ladies and gentlemen, I present to you Dr. Sasi Kumar. Please.
Thank you, Hans. Thank you for introducing Dr. Sasi Kumar. And just a request to all the participants, we'll only be taking questions at the end of the session, and you can post your questions in the chat, and we will present it to the speaker at the end of the session. Over to you, Dr. Sasi Kumar.
Okay, so thank you, and it's a pleasure to be addressing you and joining this platform, which I Ram has kind of introduced me to recently. I'm very happy to be part of this. And as was mentioned, AI was my, breathing air for from the time I started my career, which is about 40, almost 40 years back. So you might wonder that, why, the AI is a very recent phenomenon. So what is there so early to worry about? So I think the basic advice is that AI is a very old discipline, and the word AI itself is coined in 1956 in US. So and there is so much work has been done in with respect to AI in those days, and with very limited computing facilities. But so today we are all talking about deep learning and all its varieties, convolution learning and all that. But that is, to me, is addressing one aspect of AI. The AI spectrum is much bigger, much wider. And so I will try and look at one or two pieces of that spectrum to you today. And there is so much more that we can discuss later on. If you are interested, you can connect up also. Okay, so I'm with CDAC Mumbai. CDAC is Center for Development of Advanced Computing. And so we had a very active AI program during the 1985 to 95 period. We did a lot of work with what is considered the traditional techniques of AI, heuristics, genetic algorithms, and things like that. They were very effective. So it is not that these are purely academic. They are practical. They are usable for solving real-world problems. So I've kind of chosen one subset of that, which is the bio-inspired techniques. So, and if you are into computer science, this bio-inspired is not very unusual to you, because whenever we have a problem, we always look at the nature and say, has anybody in the nature has got something for us? So we look at how birds fly, we look at how animals live, we look at how plants grow, we look at how nature works, and use that ideas to build our algorithms, build our solutions. Okay. So, and specifically, I will talk about a couple of techniques which are more inspired by the way we live and we solve problems. Okay. So that's the focus. And so I'll take a minute or two to tell about where we are in AI, because that is important to understand why I'm going to talk about this. So and the answer to that is, I mean, we are doing great work with respect to a lot of domains, large language models and transformer architectures and generative AI, and all that things are actually taking the world by storm. And a lot of exciting work is happening there. But if you look at, they usually are looking at one class of problem, which are mostly of the classification type of problems, and maybe to some extent clustering. But there are a lot of other classes of problems which we don't seem to be looking at very seriously these days. But in the olden days of AI, that was a very serious focus. What practical problems in life that you see, how buses are scheduled, how ships are scheduled, how events are planned, and things like that. So I'll talk a bit from that angle, and then come to this bio-inspired techniques in computer science or AI. And specifically, I'll talk mostly about genetic algorithms and collective systems. Collective systems, you might be more familiar with it in terms of ant colony optimization and the particle swarm optimization and those kind of things. So that overall framework, I am not getting into too much detail, because the theory and the maths there might be a little heavy, and there is a limited amount of time we have. But I'll want to give you a feel of it, so you can go back and look at what is there. Briefly, I also want to talk about something that is exciting to a lot of people, called artificial immune systems. How does the human immunity mechanism work? When we have a lot of these, viruses and fungi and bacteria all around us, trying to attack us, anytime. And we have a very strong immunity mechanism which actually prevents these attacks or controls these most of the time, winning over them. So what is that mechanism? And does that make sense to look at those methodologies in order to address cybersecurity problems, for example, which is something that is bothering everybody today. So security in the online space is something that everybody is concerned about, whether it is financial or identity or whatever. And people, attacking your computer or network and trying to do things and steal information. So there is a lot of these things there. I think one of the interesting thread is to look at the human immunity framework and try to see what we can do from there. And with that, I will wrap up for today. Maybe take a few questions, and we can, of course, continue the discussion online. So in terms of, when we were learning AI, this was a kind of a mandatory section. What are the application nature or types of applications of AI? So diagnosis classification is what everybody is talking about, classifying, image or diagnosing from a CT scan, whether you have a particular disease and those kind of things. So diagnosing classification is a pretty big area. But they are of the type that given an entity, you want to assign it one label, saying, okay, you are of this type or you are of this type, right? That's basically the idea of diagnosis and classification problems. There are also clustering problem, which is when you given an unknown population, trying to get a feel of what does this population look like. So you walk into a classroom and you find 100 people, 200 people sitting in the class. And you want to ask, what is my audience like? So somebody will say, they are mostly students with a computer science background, and they are also professionals working in the banking sector. So that's a kind of thing that clustering tries to do. Okay, people have tried a lot of techniques for clustering also. Quite effectively, K-means clustering and those kind of algorithms are well known. Another class of problem which is not too much addressed is the planning and scheduling problems. So given a set of constraints that I have this much time and I have only this much money or the resource that I can spend, and I have all these things that I want to do, in what order should I do it, when should I do it, and where should I do it? So that's kind of planning. So it could be a students planning for their day. It can be a professional planning their the activities during the day, factory planning the major operations as the day goes. So planning has a very, very wide range of applications, and that is something that AI people have tried to look at it with a very traditional models in the very early stages. So there was the strips planning framework, which is simply did saying what is the difference between where I am and where I want to go, and try to minimize that difference through a set of operations and things like that. So that was the mean sense analysis kind of models that the planning used in the beginning. And one special case of planning is what is called dynamic planning. So which is that I make a plan. Okay, so I'm going to do this. And then suddenly something else comes up. You get a call from your boss saying that urgently attended the meeting and all your plan goes. So how do I adjust my plan with the least interruption so that I can accommodate changes? So railway locomotive movement or a ship movement, when suddenly there is an obstacle or there is an attack on the way, how do you adjust the plan? So it's called the dynamic planning. Then similar task is configuration, where I want to put together a bunch of things together so that they work coherently. Language processing, I don't have to tell you about that, because with LLMs and ChatGPTs and Gemini and all that, language processing is where all the focus of AI today is. And also monitoring systems. So when a system is running, keeping an eye on it, before things go out of control, how do I get to know that there are problems there? So when you say AI, you should be looking at something that can solve these kinds of problems, not just the classification or diagnosis or just text generation or whatever. Okay, so that's how we want to look at AI, and that's where this talk also makes sense. So AI today is primarily looking at classification-based problems. Gen AI, while everybody is saying that Gen AI solves everything in life, but you should understand that Gen AI is a predictive model. It only tells you what to put next given a large enough context. Okay. So this model of predictive, this predictive model has its limitation. Creating an overall perspective, constructing an answer on the fly. These are things that would be very hard for predictive models to do. Of course, people are working on it. There are things that is that is coming up. So maybe I will change this opinion after maybe some time. The results we are getting is very impressive. That is why all across the world, everybody is very excited about AI. But going to the next level, that is what is called artificial general intelligence, that is like a human being or any intelligent being, not just solve one type of problem, but solve a range of problems, being able to switch from one problem to another, use the information gathered from one problem in the context of another problem. These are things that we want to look at in order to reach artificial intelligence. And that requires you to broaden the scope to cover these other types of problems. So as of now, it is not very clear if the DL-based, that is deep learning-based approaches will actually scale to do this kind of this range of tasks. A lot of people in the research, academic and otherwise community feels that DL will saturate at some level, and we will need to look at other models to come in at that time to actually address the bigger challenge. So including, should we use symbolic approaches to look at optimization solutions and all that. So this is where I see a lot of traction today in the literature. So in that context, we can look at, bio-inspired. So as I said, biology or the biological nature inspiring computer science is not very unusual. So if you study data structures, your tree search algorithms and binary trees and different types of trees and graphs, and a lot of our models of computers that we use inside the computer are usually driven by something that we are seeing outside. Okay, so that kind of takes excitement out of bio. And if you are into yoga, you will find that lot of the yoga postures are inspired by how animals and other living things are there. So there are postures which look like trees, which look like cat, which look like dog and all that, to kind of seeing whether their level of flexibility can be brought into human body also by this kind of practice. So that's a good reference in there. Of course, it has nothing to do with AI. I'm just trying to give you that feel. And in AI, even neural network is inspired by human neural models, right? So I'm explicitly stressing the word inspired because the neural network that you use on your machine has really nothing to do with the neural structure that you have. Okay, the human neural structure is far more complicated, far more far different in the way they operate. That is chemical, this electronic, and all that. That one cannot say that the neural networks are like the human neurons, but the idea that a lot of very meagerly powerful, very minute neural nodes, the neurons, are coming together to create a human brain is what a neural network is more adopting it. So again, it is something that is not really in what I want to talk about, because AI means you would be familiar with neural network and all its variations. There are also, for example, if you look at work in the area of robotics, how do you want a robot to move? And every possible moving animal in the world has been copied from the locomotion solutions for robotics. So there are robots which wriggle their way through like a snake. There are robots which flies and jumps like insects, and there are robots which are like birds, and so on. So all the various types of locomotion that various animals are following have been tried because every movement type of locomotion has their own advantages and disadvantages. So for different terrains, walking is not always is the best way to do for locomotion. So you can find a lot of literature on this of snake-like robots and insect-like robots and all that. So let's look at something that we can do for more complex problem solving. So as I said, I'm going to look at genetic algorithms. So the word genetic algorithms, I mean, I'm sure some of you might even be familiar with this terminology and what it means. If you are a purely new generation AI, you possibly won't know much about it, but those who are into computer science earlier would possibly have some idea about it. So the word genetic means that it is inspired by the Darwinian model of evolution and the Mendelian genetics, that something that you acquire under certain conditions can be passed on to your children and so on and so on. I'll tell you more about it. So genetic algorithms has been a very immensely popular technique for optimization problems. So, and optimization problems is what most of the planning problems and configuration problems are, all basically optimization problems. Okay. So there's plenty of literature that is there in that. I'll tell you a little more about it in the next few slides. Another category is what is generally called the collective system. So there it is like a human, the neurons. Each neuron, if you look at it, is largely incapable of doing anything. I mean, it can only take the inputs and produce some kind of a sum of the input for the output, right? But what can this neuron do? But when a billion of these neurons are put together under, with suitable conditions, we are able to do almost the complexity of a human brain. Okay. So there is a much complex behavior that emerges from a bunch of these guys coming together. Okay. So collective is because unlike in other cases, it's not just one entity we want to deal with. A population of these entities, which are themselves very, very powerless, very minimal creatures, we put them together, we find that they are able to do very interesting things. So the common example is, the behavior of ants and birds, for example. So if you look at a bunch of birds flying, particularly the migration times and all that, you would think that there is somebody is giving instruction as to, what each of them should do. But no bird knows what the other birds are going to do or what is the plan. I mean, it is the route is maybe planned but for other reasons. But how do these birds actually stay together? How do they know that this bird is where that bird is going to go home after some time and all that? So there is no, manager bird or an CEO bird which says, okay, now you all turn left, now you all turn right. There is nothing like that. But they do a pretty, amazing job of doing that. And similarly, if you look at ants, gathering food and taking, small food particles to their nest, again, there is no coordination in the sense of, somebody saying, okay, we will take this piece together, three of you will come in the behind, the four of you will go to the front, and then we will grab. There isn't anything like that, right? But if you watch those bunch of ants carrying, a piece of bread or, a grain of rice, you would think that they are under instructed by somebody. Okay. So this behavior, which we believe is the emergent behavior, which is not programmed by anybody, by coming together of a bunch of these, is what basically collective systems are doing, are inspiring us to do. So these are inspiring because, for example, you keep, let's say, some sweet somewhere in the corner of your house, the ants will get there. And then everybody will follow. One ant, two ant will get there, and then the whole bunch of ants will come there. How did they get to know this? How did they tell all to come there? So this is like a pathfinding problem, which is something that, we are all interested in planning, scheduling kind of applications. So genetic algorithms and collective systems are very, very interesting bio-inspired techniques. And there are also a lot more, as I said, artificial immune systems, which tries to look at the human immunity mechanisms and try to see whether that can be used for cybersecurity and other things. Cellular models, which is cell level. So this is also very, very interestingly inspired, because the other day I was reading a book called The Song of the Cell, and I would actually recommend to you, if you can find the courage to read it, because it is a lot of biology and a lot of physiology and all that. But it is actually telling about how the human body, or the human body, has a collection of cells. It is not that for example, the cell in my brain doesn't know that the body exists, right? The cell in my finger doesn't know that the hand exists, or the leg exists, or the eye exists. So every cell is pretty much independent, and there is no, as I said, a manager or a CEO sitting there. But these maybe a billion cells, they just work together beautifully, so that you can walk, you can eat, you can talk, you can listen. All of this is there. So it's an amazing model. And when you want to look at the scalability and all that, so that is there. So these are some of the things. I think there is a lot more, but in the interest of time, I'm going to stick to this. Now, one notice, as I mentioned in the beginning, it is bio-inspired. So we are not saying that we are ant colony optimization does exactly like what the ants do, or genetic algorithms do exactly the way the evolution works, or whatever. We are trying to look at the key idea there, and then try to adapt it, massage it, so that I find I can implement anything that you should keep in mind. So, genetic algorithm, as I said, Darwin's theory of evolution says how organisms evolve from basic structures. So, from basic structures to complex structures, and even as human beings, or as one type of things, evolving in terms of capability over a period. And it is important to notice that, we are not talking about most of these cases that, in 2-3 iterations, you will get a solution. Nature has taken maybe millions of iterations to produce, entities like us. Okay. So it is because to a large extent, genetic algorithms is something that you would wonder, how does it even work? Because, there's a whole bunch of these entities in around, which kind of spontaneously make random modifications, and eventually, maybe a human being comes out at some point. Okay. And with the kind of complexity that we have. So this is a purely statistical kind of implementation when you look at the code. But the key ideas that I mentioned below there, one, organisms compete for some constrained resources. Okay. So in the normal world, it is the limited amount of food, or there is a limited amount of space, and there may be a larger number of candidates there, and they have to fight to get to use it, or get to consume that food. So when you want to fight, when there are 3 people fighting for something, the strongest, the fittest one will win. Okay, so that is the survival of the fittest. The ones which are able to win will survive longer. Okay, so and those ones which are surviving presumably has some attributes in their genes which is giving them that higher strength. And therefore, when they reproduce, this capability or this genetic changes also get passed on to their offsprings, who in turn might make more changes. Right? And each of these individuals can come up with their own modifications, the mutations and crossover that they do. So it is this 4 things together which gives you a roadmap of how evolution would have taken you to this place. Okay, so we can look at this evolution as a computational model to improve the fit of the organism to the surviving. So we are not worried about survival or food, but we are going to map that into computational characteristics. So when I want to, for example, a traveling salesman problem, or a vehicle scheduling problem, my food here is the amount of fuel that is getting consumed, for instance, or the total distance traveled by all the vehicles put together, or the total number of passengers that has been carried. So I can map food into some of these kind of things, or the space or whatever. So I'm going to map these key parameters of food and these genetic changes in computational terms. Now, organisms means what? So I'm no longer talking about living organisms with blood and bones and all that. But an organism is a simulated entity in my system. Okay, so I can talk about, for example, if I'm going to do find out the best routing plans for a city, let's say all the buses in the city, every routing plan that has come up is an organism. Okay, is one plan. Now, which of these plans should be best? So that's where I look at the number of passengers carried, the number of people, time people wait, the amount of fuel used. They will be my fitness criteria. Okay, so I can evaluate the various plans I have, order them based on the fitness criteria, and then I'll say, okay, these are the best ones that I have. So let they reproduce. What is reproduction now, or what? How do I create the next generation? I take the existing solution and do some minor changes. Okay, because major changes can actually set the whole schedule. So usually you make minor changes. So I will say, okay, instead of bus number 34, let us put bus number 36. Okay, or instead of 34 going to this location ABCD, let it go to location XYZ. I'm not changing anything else there. So these kind of changes, what we call mutations, actually are introduced, and with this mutation, the fitness may reduce, it may increase. So I re-evaluate it, and then I choose the better one to survive. So very, very broadly, that is the model that we are talking about. So first, on the right side, you see create a population of candidate solutions. So let's say I create 100 random solutions. Okay, so and this need not follow any particular rules or optimality or anything. Just create some X number of bus routes and send it to some random locations. Okay, so I have an initial population of solutions. And here it is important that these candidate solutions are not very uniform. They should actually be as different as possible, right? Because otherwise it is like where you are looking at one type of solution and you don't actually explore the possible search space there. And evaluate the fitness of these solutions. Okay, how good do they solve my problem? Do they actually lift more passengers than the other solutions? Do they use less fuel? So I evaluate their fitness, and then choose maybe something like the best N out of that. These solutions, I will get them ready for the next generation. Okay, next generation is basically copies of these solutions with some modifications. So if you look at the simplest way of looking at a solution is just a binary vector. This 1 0 1 1 1 1 possibly says that whether this person is selected for the job or not. Okay, so maybe something like that. Or this route is operational or not operational. So let's say 1 1 and 0. And similarly, the next row is another solution. I can create a crossover by taking row 1 and row 2 and say, I will take the alternate bits from the two solutions. So the first bit I'll take from the first solution, the second bit I take from the second solution, the third one I take from the first solution, the fourth one I take from the second solution, and so on. So what is happening? I am trying to borrow some properties of both these solutions. Okay, that is the advantage of crossover. It allows you to learn from multiple solutions, multiple parents, and exploiting both of their characteristics. Of course, at this point, I don't. Okay, so it's possible that when I do this merger, the resulting solution is worse than the previous one. But in some cases, you will also find that they are doing a better job than that. Similarly, mutation is to take just one or two elements and just randomly change it without affecting anything else. So this last one, when I create this mutation, I might just change it to 0, but everything else remains there. So this is very simplistic way of explaining it. I mean, there is a lot of studies about different types of crossover, different types of mutation, different types of population representation. That makes genetic algorithms quite interesting. And I think there are whole book written on GA that you can look up. Now, once these some solutions are generated, you have a revised population. So I started with one bunch. Now I have, let's say, n solutions were there. I may create, let's say, 2n solutions or 3n solutions, rank them and choose some appropriate subset. It's not always the best end that I will choose, because sometimes choosing something that doesn't look good might be a good idea because it might have some interesting property in it, which I can later on build on that. Okay. So again, you can see a lot of what looks apparently like an ad hoc way to do it. But the idea is that to provide as much breadth and depth as possible in the way I do things. So if I want to optimize based on some set, I want the set to be as broad as possible, as different as possible, because more difference they have, they are coming from different some parts of the search space. Okay. And therefore they bring in different properties or different requirements. Similarly, when I want to, like choose the set of people to be moved to the next generation, mostly I will choose the best ones because they are the ones that I have created and which looks promising. But add a one or two which are not so good. They provide an additional variety in the next generation. So this is the basic loop. We keep iterating it till you find the solutions which satisfies adequate adequate quality in terms of fitness. Okay. Or your the entire population converges. Nothing is improving. Maybe there's a plateau. You can't actually go beyond that. So GA in practice is very effective for large search spaces from which a good solution is required. It is very important to remember that because of the nature of this algorithm, there is no guarantee of finding the optimal solution. Okay, because we are basically exploring in the search space and trying to jump into something a little higher here, little higher there. Eventually, we will get to something that is good. But the actual peak might may not be reachable through this mechanism. And most AI problems or most practical problems do not require the absolute peak. I mean, as long as you are getting something that optimizes, like for example, if the peak of, let's say, bus route scheduling is to take 95% of the population, that is, I mean, the passengers who are interested, if I get to 94 or 93, that might also be good because we don't know how to reach that 95. Okay, what combinations would help us to do? Okay, so that's also an assumption that we are making. So, and the reason why you don't get to the optimal solution is, I mean, unless you have a very simple hill, you put something there, it just keeps climbing up, it will reach the top. But in real life, there will be lots of valleys and sub-optimas and, all of that. You don't have any idea where the actual optima lie in your search space. So a lot of improvisations have been tried to improve the performance. I had also worked on a lot of interesting crossover solutions and all that for some of the applications that I did on. And there is, as I said, good amount of literature. You can actually read up more about it to understand the complexities and how this is used. So implementing a GA means one, you have to decide a population size. Too many samples and the population is a very rich object, then handling them and the generations, etc., can become very expensive. So you want to choose something that is not too small. If it is too small, there will be no variety to explore. If it is too large, it will become too unwieldy to manage. So you want to choose something that is reasonable. Usually, in many cases, it is like a 50 or 100 population size is good. Instance representation. So what I showed you there in terms of a simple binary vector, that binary vector may not be the way actually the entity behaves. Like the human genes, the DNA, the RNA that defines us, doesn't actually look anything like us, right? It's a double helical structure of amino acids, right? So like that, your population representation can be very abstract and something that is easy to manipulate from a crossover and mutation point of view. The phenotype is how that entity will actually behave in practice. So, for example, again, if you take the bus route scheduling, every route, I will say whether that route is on or off. That is how my bus route plan is decided. Okay. Given this plan, now I will go and check whether how many passengers are taken care of by them, what is the total distance travel. All of that I compute, and that defines my quality measure, the phenotype. Okay, so the genotype or the representation should be chosen carefully, because otherwise implementing crossover mutation, etc., can become very challenging. And initialization should be random. You should span this random sampling across the space as much as possible. So crossover and mutation, I already told you, combining two individuals to generate a third one. And the assumption is that when you do these two individuals and generate a bunch of them, at least some of them will do better than both the parents. Okay, that's what we want to do in crossover. And mutation is random changes in one individual, particularly when the population is getting stuck at some local minima. This kind of changes would actually throw you out into some other place so that you can actually start exploring that space better. So why does it work? The fitness function is the driver. So like, depending on the type of exams that you face, you decide how much to study and what to study, right? So if it is all multiple choice exams, then it will be one thing. If it is open book exam, it is another way of studies and so on. And but on the other hand, there is something called a schema theory, which has been proposed to provide some formal explanation for how this thing works. So basically, the idea is to look at every instance of the population as sampling a large part of the search space. Okay. So again, I won't elaborate too much here, but you can look up the material on schema theory, and it has some interesting association. Collective systems, that is the second topic under this. So the basic idea is that a number of simple processing elements working simultaneously can produce emergent behavior. So flock of birds, school of fishes, and all these are there. So there is no global or supervisory direction of management, and that is what is interesting there. So it's easier to implement it in a distributed form. So particle swarm optimization, non-colony optimization, robotic swarms, and there are a lot of other variants that people have explored, which gives you an idea. So what do we do from this? So you can ants looking for food, something that the ants can smell. And the more pheromone on a trail means that a lot of more ants have gone through this way. So most likely there is more food here. Okay. So we can also, when you are traversing a graph or a tree, you can also deposit some parameter or some weight on that edge you can do. That is our pheromone, right? And every time somebody goes through that edge, you increase that weight by a little bit. Okay. So this is how we borrow these ideas from foraging of ants. And there's also some rare loudness of cry. So I listen to the sounds being made by other animals of my category and look at the loudest one, and then I pass it on to others around. Okay, so because louder cry means that much better quantity of food is available. So these are all some models of communicating. So what is called the stigmergy, the cue-based communication, right? So, and people have also adopted this idea that, for example, the pheromone one, if so many ants are going on a long path, everybody will start following that long path because of this behavior. So if you want to stop that, people have invented this idea of evaporation of pheromone. So If once, for a long time, if there are no activity on a link, the pheromone levels can automatically drop, or the weight on the graph can be dropped. So this is how we convert these ideas from nature into software implementations. So as I said, cellular systems, Conway's Game of Life, which is a very old system, that is able to model a lot of interesting properties of life. Isolation, starvation, social behavior, all of that, which is very simple, game of life game. And immune systems, which is interesting. I mean, maybe another time I'll tell you more about this. So these are all models that we can actually follow. Okay, so I think let me try to kind of. So there is a lot more to AI beyond the DL-based solutions, the deep learning-based solutions. So I always talk about AI from the non-deep learning aspect, not because I don't believe in deep learning, but because there is a bigger space out there, and challenges associated with the deep learning. I mean, if generating explanations and things like that are also something that AI people should understand. Nature and human way of solving problems always has been an inspiration to build artificial systems to solve a problem. So it is not only computer science. We always look at nature for inspiration. This inspiration is then adapted for a computer implementation. And that is it is interesting. We are not just copying from the nature. Like maybe the first version of aeroplane was possibly tried to do with flapping wings, but we have evolved. But although birds have inspired that, but our aeroplanes have very little similarity to how a bird flies, for example. Okay. But these approaches, there are a lot of success stories, a lot of material in the literature. So I think if you go and do a little bit of exploring, you can get to know more about all this. Okay, so I think I will stop here and take maybe a few questions also, and then I'll wind up. So thank you for the listening. I hope I was audible to you all the way through. The slides I'll be happy to share with you if anybody wants. Thank you.
Yeah, thanks, Mr. Shashi Kumar. I'll just pick up a few questions posted in the chat here in the Q&A session. Then
Okay.
one of the attendees is asking, how do you see this field evolving over the next few years?
This field meaning this bio-inspired.
Yes.
I think I believe these things have a lot of potential because, as I said, the AI that we are practicing today do not actually solve the entire range of problems. So particularly when it comes to pure optimization problems like planning, scheduling, configuration, and those kind of things, you will need to look at some of these models. And even the age-old heuristic search techniques, I mean, I have worked on using that to solve some scheduling problems. Yeah, I mean, they have their own limitations, but then there is really nothing better that we have. There is the very brute force search that IBM and Google and all that have done for those game applications. But that is, I don't know to what extent can that be copied or adopted for practical problems. Games is okay, one part which we understand very well, so you can create the search space, but others we don't know. Okay, so yeah, so so my feel is that these are going to be important as we go further. Oh yes, yeah.
Okay. One of the attendees is asking, like, how do biologically inspired algorithms perform compared to other methods?
So again, like most AI algorithms, there are no universal answers. So one is the nature of the problem, the characteristics of the problem, the nature of the search space, and the kind of operators you choose. For example, genetic algorithms is not a given solution. You still have to figure out how to represent the population. You have to figure out what is the right kind of crossover and mutation. There are a lot of very open areas. So you can explore a lot of these. So you can, at one point is that we cannot say genetic algorithm works or not. Your particular implementation may or may not work compared to other solutions. But then you come back and say, okay, what can I do? For example, why is crossover not really producing good quality solutions? Maybe there are dependencies, for example, if the individual, what is called the alleles in the population, they have dependencies amongst each other, then these random mutations and crossovers can actually mess up your solution. So these things you will need to understand. But as a technique or an algorithm, I think they are as good or better than these other algorithms for certain kinds of problems.
Yeah, and thanks, Mr. Shashi Kumar. Uh, another attendee is asking, what kind of industries do you feel they're most likely to benefit from these algorithms? Like, I think what kind of which industries and which use cases could we probably use this?
So I think it is not about industry. It is about the nature of the problem. So as I said, most of the time we are looking at let's say if you look at the traditional AI models, we have a huge amount of data, decent quality and adequate in quantity. And the problem is more of a classification or predictive models. Then it is the current models are pretty good. But if you want to do, for example, a factory optimization, or you want to do scheduling people for different tasks in a factory, or scheduling buses in a city, or trains, or aeroplanes, or allocating people to a project. So these kind of problems are there in pretty much any company or any industry. So if you have these kind of problems, these techniques are good candidate. So I won't say that manufacturing mate is good, but finance mate is not bad. No, it's not. Even finance, for example, what would be a good investment portfolio for my nature, my risk taking nature, the amount of money, the requirements I have. If I want to get a package of how I should put my money into various options, what will get to? I don't think Gen AI kind of models can answer that question. So look at the problem, map the problem to this technique rather than specific industry.
And one more, we take this last question.
Yeah.
We have one of the attendee asking about any ethical considerations. I think it's generally not pertaining to.
No, there is no ethical because I'm only simulating it. I'm not using any animal characteristic, or I'm not taking anything which is very, very unique to that. I'm only looking at the way that animal works and say, oh, maybe I can write my program which mimics that behavior. So I don't see any ethical problems in this.
Okay, Dr. Sasikumar. And Hans, thank you so much for guys to joining us. And to all the participants, please visit us at iabse.org to become an authorized training partner with IABSE. And we'll keep you all informed and posted about our upcoming events by email and across all the social media platforms. And looking forward to connecting with you all soon. And thank you all for attending today's session. And have a nice day. And thanks, Mr. Sasikumar. And thanks, Hans, for joining us. And goodbye, everybody.
Thank you. That was a great opportunity. Thank you very much.
Thank you and goodbye.